Hello my dear students, this is Akash SD. Welcome to the ASD physics classes. Hope so you all are doing really great. So students, in this video we are going to learn about the Biot-Savart Law and the questions and derivations based upon this. Okay, so let's start the video. So here you can see in Biot-Savart Law we are going to see magnetic field due to current element. Okay, so let's first see the introductory part and all that. Okay, so see here. This experimental law, this is the which law? Experimental law. We have got this law by the experiment. Okay, so this experimental law deals with the magnetic field produced at a point P due to a small current element IDL. Okay, so here you can see the current element I am writing I into dl. I is the current and dl is the very small length along the direction of the current. Okay, remember that current is a scalar quantity, but current element, that means I into dl is a vector quantity and always along the direction of the current. Okay, great. Now let's see here the situation. Let current I flows through an arbitrary shaped conductor as shown in diagram. So here you can see the conductor is arbitrarily shaped, that means not straight line, not circle and all that, na? Normal arbitrary shaped here. Now see here, magnetic field dB, magnetic field dB at point P at a distance small r from the current element ideal is given by. Okay, so here you can see we are going to calculate magnetic field dB at which point? At point P. How much distance? Small r distance from the current element. Okay, so just let me draw here now. So let's take, for example, the current is flowing in this direction. Now this is the direction of the current flow. Now what will happen that here, students, if I will take here the very small current element, let's take here. Now here I am taking very small length dl. Okay, so that small length dl will have current element in this direction. Okay, just let me draw here like this here. This is called what? Ideal. Ideal. Okay, very small length dl I have taken. Okay, now after that let's take here, here is the some observation point P is there, is it? And this observation point P is having some position vector r. Now current element to the observation point, one vector we are drawing, that is called what? Position vector r. Now and let's see here the angle between current element, that means ideal, and the position vector is how much here? Theta angle. Now remember that here again I am telling that here ideal means very small length dl, current in this direction, so we will just draw here one tangent, that will be ideal current element. R is the position vector pointing towards the observation point from the current element, and theta is the angle between a current element and the magnetic field. Okay, now you know very well magnetic field is the which quantity? It is the vector quantity, that means it will be having some direction also. Magnetic field is the which quantity? Vector quantity. And how to get the direction? Very simple. Always you have to curl all your fingers of right hand along the direction of the current, palm towards the observation point, then thumb will indicate the direction of the magnetic field. Okay, so see here, all my fingers along the current, my palm towards the observation point, then this thumb is which side? Inside. Okay, again and again I will use this here. Again I am telling that here all the fingers along the current, palm towards the observation point, then thumb will indicate the direction of the magnetic field. Okay, so in this situation remember that here magnetic field at point P, by the experiment we can write here this dB is directly proportional to I dl sin theta by r square here. Okay, this thing you have to remember that here by the experiments we have got here. I is the current, dl is the very small length, theta is the angle between current element and the position vector, and what is small r? Small r is the distance from current element to the observation point. Okay, so remember that here. First we are writing here in a scalar form. Okay, later we will write in a vector form also. Okay, great. Now students, let's see here, after that see here in free space, or we can tell vacuum, applicable for air also. So let's take for example this current carrying conductor is placed in a vacuum or air. Okay, so in this situation remember that here when we will remove the proportional sign, proportionality constant will come. What is the proportionality constant mu naught by 4 pi. Okay, and we can write here I dl sin theta by r square. Okay, this is dl. Okay, I dl sin theta by r square here. Okay, where in air. Okay, and this mu naught is called permeability of a free space or permeability of the vacuum. Okay, similarly, if we talk about here the SI unit here. Okay, so what is the mu naught by 4 pi? Again, I am telling that here this is the proportionality constant. What is there, students? This is the proportionality constant. Proportionality constant. Okay, proportionality constant. This mu naught by 4 pi ideal sin theta by r square, is it? And mu naught by 4 pi is the proportionality constant. Now, remember that here if we talk about this proportionality constant in a SI unit, so remember that here this mu naught by 4 pi in SI unit, it used to be 10 to the power minus 7 Tesla meter per ampere. What we can write here? 10 to the power minus 7 Tesla meter per ampere. Okay, even we can write here, remember that here 10 to the power minus 7 SI unit. Now even we don't remember this also, we can write 10 to the power minus 7 SI unit. Okay, now students, after that, very important in a CGS unit. Which unit? CGS unit. So remember that here in CGS unit, this mu naught by 4 pi is given by, we are going to see it will come 1 CGS unit. How it will come here? See, I can write here, see 10 to the power minus 7. Now after that, Tesla means, remember that here 10 to the power 4 Gauss. Tesla means how much here? 10 to the power 4 Gauss. Meter means 100 centimeter, so 10 to the power 2 centimeter. By ampere. Ampere means SI unit of the current is the ampere, but CGS unit is the Biot, BI, or even we can tell ab ampere also. So remember that here ampere means it is given here 1 by 10 Biot, BI, is it? So what will happen that here when this 10 will go in numerator, we can write here, see 10 to the power minus 7 into 4 plus 2, 6 power something exponents. This 10 will go up 10 power 1, so 6 plus 1, 7. No? So it will come 10 power minus 7 into 10 power 7 Gauss centimeter by Biot, is it? And when you will simplify this, what this will come here? It will come here 1, and we can write here 1 CGS unit. No? Or we can tell here 10 to the power minus 7 SI unit, or just one CGS unit here, is it? Similarly, if we talk about here in electrostatics also, so in electrostatics, proportionality constant used to be 1 by 4 pi epsilon naught. Value 9 into 10 power 9 SI unit. But in CGS, how much here? 1. Is it? So similarly. Now students, after that, very important, see here, in a vector form. So vector form of Biot-Savart law, now very important. So in vacuum or air, remember that here, it is given here dB equal to, very important, mu naught by 4 pi I dl cross r cap by r square. Okay, r cap by r square. Again I am telling that r cap means by r square. One more form is there, remember that here, mu naught by 4 pi into I na vector dl cross vector r by r cube. So r cap means by r square, vector r means by r cube. And what is mu naught? This mu naught is the permeability of a free space. Okay. Similarly, if in case this current carrying conductor is placed in some medium other than vacuum. Okay. So here what will happen that here? Remember that here I am going to write here. No, I am going to write here dB equal to, instead of mu naught, I will use just mu. So mu by 4 pi into I dl cross r cap by r square here. So in vacuum or air, mu naught, but in some medium, instead of mu naught, what I will write here? Mu. And what is mu? Mu is called permeability of the medium. Okay, and I hope so one thing you know very well here, this relative permeability is given by permeability of the medium by permeability of the free space. Okay, and from here also you can write, see here, this mu equal to mu naught into mu r. What we can write? Mu equal to mu naught into mu r. And similarly for air, if we talk about here for air, just think and tell what is the value of the relative permeability. It will be how much here? 1. Is it, students? So I hope so. This Biot-Savart law basics is the very clear to you. Is it? Especially this one here, 10 power minus 7 SI unit and 1 CS unit here. Okay, great. Now students, let's see here some special conditions are there that will be useful when we are solving the numericals. Okay, so see here, special condition of Biot-Savart law. So see here, if observation point P is along the length of current carrying conductor, again I am telling, along the length of a current carrying conductor, then magnetic field at that point will be how much here? Then magnetic field at that point will be 0. Okay, how can I tell that here, students? Kindly see here. Let's take for example, here the current is flowing I, no? And here let's take in this direction, I have taken very small length and this is the current element. IDL here. Is it? Very small length DL. After that, let's take here for example, if I take here, this is my observation point P. Is it? So, and making how much angle? Let's take for example, this angle is theta. Is it? So what will happen that here, if I take here, my observation point is here. Let's take at point M. Is it? So you can see point M is along the direction of the current. Is it? So you can see very well, if this point P is becoming M. Now, so what can I tell here? If the point P is becoming M, so what we can tell is, students, tell me, at point M, what is the value of the theta? Think, na? When the point P will move in this direction, theta will keep on decrease. At point M, theta will become how much here? 0 degree here. Okay, that means if I write here the magnetic field at point M, that means along the direction of the current. So dBm equal to what is the formula? By default, in air, mu naught by 4 pi I dl sine theta means sine 0 by r square. Sine 0 how much here? 0. So what will happen that here? Magnetic field will be also how much here? 0. Is it? So when the observation point is along the length of current, magnetic field will be 0. Similarly, if in case I take in a reverse direction, let's take for example here, na? And I have taken point N. Which point is there, students? This is the point N. Then what you think at point N, what will be the value of the theta? Now, we are seeing the angle from here. Now, so here theta was 0. Here theta was how much here? 0. But when we are going in the reverse direction, theta will be how much here? Theta will be 180 degree here. Is it? Because this is the reference line, and see, angle is keep on increasing at point N. Is it? So what we can tell here, students, here at point N even. At point N, theta how much here? 180 degree, and you know very well sine 180 also how much here? 0. So as sine 180 is 0, again magnetic field at point N will be also how much here? This will be also 0. So very important, whenever observation point is along the length of current carrying conductor, maybe forward, maybe backward, what will happen? Magnetic field will be 0. Okay, great. Now students, let's say here we are going to see one very important derivation itself, important for the board exam. Kindly see here. Magnetic field at the center of a current carrying wire. Okay, at the center of circular current carrying wire. Okay, so here, let current I flows through a circular coil of radius r as shown in diagram. Current is I, radius is r. Now, let's see. Magnetic field dB at the center due to current element ideal of the coil is given by. So what we are going to take? I am going to take very small current element ideal. Is it? So see here. So students, let's take here, this is the center, no? And let's take a current element in this direction, very small length dl. So this is the current element ideal. Is it? And if we talk about here, this one here, see, this is my what? This is my position vector r. You know very well, tangent and radius will always make how much angle? 90 degree. Is it? So here I can write here, this theta will be how much here? 90 degree. Is it? And the current is flowing in this direction anyhow. No? Current element this side I have taken. So anyhow the current is going in this direction like this. Is it? And what we are going to do? We are going to find out a magnetic field at the center O. Is it? So again, what can I tell? Magnetic field at point O due to current element ideal is given by very small magnetic field. It is given by dB equal to, see here, mu naught by 4 pi by Biot-Savart law. Ideal sine 90 by r square. Sine 90 value how much here? 1. Is it? That means we can write here, see, magnetic field is given by mu naught by 4 pi into ideal by what I have taken here? I have taken here actually the capital R, okay? So I will write here capital R. What I will write here, students? I will write here the capital R here. Is it? Not a small r here, okay? Capital R, is it? So we have written the magnetic field due to this very small element, but what we want? We want magnetic field at the center due to complete wire, due to complete circular wire. That means what we have to do? Due to each and every current element, we have to calculate the magnetic field. Then by using the integration, we have to add it here, is it? And even at any point of this circle, you take current element and the position vector at all the points, it will make how much angle? 90 degree, is it? So what we can write here, see here? Magnetic field B at the center of the coil can be calculated as here, okay? So what we can write here, see? Magnetic field at the center of the coil. That means due to each and every current element, we have to do the integration. Closed coil, so closed integral dB, is it? So now what we can write here, see? Closed integral dB mu naught by 4 pi here I dl by r square, is it? And what are the things are constant? So mu naught by 4 pi into I by r square is constant, is it? That means what we can write here? Closed integral dl. So you know very well, if you add all this small length dl, what you will get? You will get the circumference. You will get the circumference of the circle. And circumference of the circle, how much here? 2 pi r, is it? That means I can write here, see, it will become here mu naught by 4 pi I by r square. And what will come here? 2 pi r, is it? Now we can cancel the things. Let's take this pi cancel. From this r, 1 r cancel. And we can write here 2 2 is a 4, is it? So hence magnetic field at the center of circular current carrying coil is given by mu naught I by 2r. What is this? Mu naught I by 2r. Kindly remember the formula. Mu naught I by 2r. Okay, directly I will use it. Okay. Now students, after that here, as nothing was mentioned, so how many turns was there? How many turns? How many turns was there? Only single turn. But if in case for the coil of n turns, each of radius r, each and every turn is having radius r and number of turns are n. So in this situation, remember that here, this magnetic field will be multiplied by n times. So mu naught n I by 2r, okay? And you know very well, when the number of turns will increase, what will happen? The length of the wire will keep on increase, because you know very well, if each and every turn is having radius r, so single turn, total how much circumference? 2 pi r. 2 turns, how much circumference? 2 into 2 pi r, that means 4 pi r. So if in case the radius is fixed, what will happen? When you are increasing the number of turns, the length of the wire will also increase, because this concept is important, because sometimes length of the wire will keep on increase and the radius will be fixed. In second case, question used to come when the length of the wire will be fixed and they will ask the magnetic field. Okay, so there we have to use little bit different concept, is it? So remember that here we have got this one here, mu naught Ni by 2r here. Okay, now let's see, this question is there, because question used to come in the exam. What is the question? See, 2 ampere current is flowing in a circular loop of radius 1 meter. Magnitude of magnetic field at the center of circular loop will be how much here? In Tesla, because SI unit of the magnetic field is the Tesla, CS unit Gauss, is it? That we have seen it. So remember that here in the question, what they given here? They have given current is given 2 ampere, okay, and the radius they are given here how much here? 1 meter, is it? So we know very well here, no? Magnetic field B equal to, nothing is mentioned, so mu naught I by 2r, is it? So what we can write here? We can write here, see the students here, this B equal to, we can write here mu naught value 4 pi into 10 to the power minus 7, because mu naught by 4 pi is 10 to the power minus 7. So mu naught means 4 pi into 10 to the power minus 7, is it? And the current how much is given here? Current they are telling 2, is it? By 2, radius how much here? Radius is the 1, is it? So this 2 and this 2 is cancelled, is it? So what this will come here? The magnetic field at the center will come 4 pi into 10 power minus 7. Tesla. Is it? That means here in a NET kind of question, what we can fill here, students, we can fill here what, 4 pi into 10 power minus 7. Is it? Can you see here? No? Very basic question. Very basic question. Is it? Correct. Now let's see here. One more question is there. No? This question is also important. See here. When current flowing in a circular loop is doubled. What is doubled? Current. Current is doubled. And the number of turns. And the number of turns of the coil in it is halved. No? Then magnetic field at its center will become how much here? Is it? So let's see here one by one. Depending upon the question, let's take here what is given. Let's take initial current is I. Is it? And what they are telling that here, the current, what is happening to the current? Current, they are making it double. Now current is doubled here. So what will become here? The current will become here 2I. Is it? After that, if I talk about here the number of turns. So let's take here number of turns is N initially. And after that, how much becoming here? Halved. That means the number of turns, they are making it N by 2 halved. Now radius, anything they told about the radius, that means anyhow radius they did not tell. So initial radius is also R, final radius is also R. So we can tell anyhow this radius is a constant. What is this, students? This radius is constant. Now because we should know very well what are the constant things and all this there. Now what we can see here, we know very well here S, see, B equal to mu naught for number of turns, mu naught Ni by 2R. Is it? What are the things are constant? Mu naught anyhow constant, mu naught is constant, R is constant, and 2 is also constant. So we can write here B is directly proportional to Ni. B directly proportional to what here, students? Ni. Is it? That means I can write here, see, this B2 by B1 is equal to N2 by N1 into I2 by I1. Is it? Now after that, what we can write here, see, what is the N2? N2 is N by 2 and N1 is N. Is it? So we can write here, see, N by 2 by N. No? And I2 how much here? Current I2 is 2I. Is it? And initial current is I. So what will happen that here, when you will see properly what will happen that here, anyhow all these things will cancel out here. Now even I can write here, see, N by 2N into 2I by I. Is it? So I cancel, 2 cancel, all these things will cancel. See, NN cancel, I cancel, this 2 is also cancel. That means what this will happen that here, we can write here B2 is equal to B1. Is it? That means magnetic field will change. It will not change. So it will not change means what will happen? It will remain same. Is it? So remember that here in this situation we have just used here the number of turns, current and all, how it is when doubled, halved and all that, how the magnetic field will change. Even if they are telling the radius also, so there also you can write B directly proportional to Ni by R. Is it? And then you can use all these basics and all that. Is it? Great. Now students, let's see here, very important, very important. No? That's why I was telling that you, this one, see. A circular coil carrying a certain current produces a magnetic field B naught at its center. Is it? Now see, the coil is now rewound. The coil is now rewound. That means the length of the wire is changed? No, the length of the wire is same. Okay. So if in case one turn is having, let's take for example, the length of the wire is for example 5 meters. So here also you are making n turns. In that also the length of the wire will be how much here? Same length here. Okay. Now see, the coil is now rewound so as to have n turns and the same current which passes through it. The new magnetic field at the center is how much here? Okay. So first what is given here in this situation? Let's take the current is I now, and here magnetic field is there by the right hand curl rule, all the fingers along the current, palm towards the observation point, thumb is inside. So anyhow the magnetic field will be inside B naught. How many turns are here? The number of turns are here 1. Is it? So initially what they are telling that here, this B naught is given by 1 turn is this, no, see, mu naught I by, I am writing here, mu naught I by, I am writing 2R naught. Is it? And the radius, how much I am taking here? Radius I am taking here, students, R naught. Is it? Great. Now after that the new situation. Here what is happening at in this situation, in each and every turn, Now, in each and every turn, the current I is flowing. Now, n turns are there. Here I am just showing for the 3. Now, but n turns means what will happen that 3 turns means the current will be become 3I. Due to 3I, the magnetic field will be there at the center. So, due to n turns, how much magnetic field will be there at the center? Ni. Is it? Current effect I am telling you. After that, do you think the radius will be same? No, the radius will not be same. Let's take the here radius is r. But remember that here, students, in both the situations, as the length of the wire is fixed. So here length of the wire how much here? Think and tell. Here the length of the wire is how much here? 2 pi r naught here, na, because circumference. Here length of the wire how much here? You know very well. Due to one turn, it is the 2 pi r. And like that, how many turns are there? N turns are there. N turns. So we can write here n into 2 pi r is the length of the wire. And here how much here? 2 pi r naught. So what we can write here? We can write here r equal to r naught by n. Very, very important, na, because length of the wire is fixed. Now after that, if I write here the magnetic field here, magnetic field at the center. So what can I write here? See, B equal to mu naught. How much turns are there? N turns. And each and every turn, how much current? I. So mu naught Ni by 2R here. Is it? R. And what is the value of the R? R means R naught by N. Is it? So see here, R naught by N. So when you will simplify this, it will come here N square mu naught I by 2R naught. Is it? And let's take for example, this is equation 1. So mu naught I by 2R naught, how much here? B naught. So what we can write here? Remember that here, this B will become here N square into B naught. What will become B? N square into B naught from 1. From 1. So remember that here, that only I was telling you, if in case the length of the wire is fixed, then in that situation, the magnetic field will become N square times here. What is fixed? The length of the wire is fixed here. Okay, great. Now, students, after that, here anyhow, no use, is it? And let's take here. For example, in this situation, what is given here? Now, let's take length of the wire is L. I'm telling you, now, length of the wire is L. Now, and we have make a circular coil, now, of a radius R naught having current I. Is it? So let's take for example here the magnetic field. How much here? In this situation, let's take magnetic field is B naught here. Is it? We know very well mu naught I by 2R naught. But let's take what is happening that here, the same length of the wire in second situation. Same length of the wire. Now is made how many turns here? Let's take a 3 turns are there. How many turns here, students? 3 turns are there. Now, so 3 turns. 3 turns are there. Is it? And here what is happening anyhow? The radius is R. Then what you know? The magnetic field is given by N square B naught. Directly have to use the formula here. Is it? Because length of the wire is fixed. Is it? And how many turns are there? 3 turns are there. That means you can write here. Very, very important. 3 square into B naught. Hence magnetic field will come here 9 B naught here. So when the length of the wire is fixed, we have to use the formula N square B naught here. Is it? Great. Now students, let's see here, we are going to see for some arc and all that. Now this is also important. See, magnetic field at the center of circular arc. Is it? So let's see here. Let current I flows through a circular arc of a radius R subtending angle theta radian. Keyword is theta radian. Okay, at center. Then magnetic field B at the center is given by. Okay, so what I am going to do here, I am going to take here some arc is this, no, arc, that means this is a part of some circle, is it? This arc is this, let me draw here, is it? This arc is this, how much current is flowing? The current is flowing I, is it? And this arc is subtending some angle, this arc is subtending some angle theta, is it? So what will happen that here, the magnetic field, let's take here the point is O, magnetic field anyhow in which direction? All the fingers along the current, palm towards the observation point, thumb inside, is it? So anyhow the magnetic field is inside here, is it? So what will happen that here, students, at this point, the magnetic field is given by, remember the formula, just I am writing the formula, it is given by B equal to mu naught I theta by 4 pi R. What is this? B equal to mu naught I theta by 4 pi R. What is this? R is the radius of this arc. The radius of this arc. And even no need to write here even B naught again and again. Is it? B is enough. Now, great. So this is the formula. Can you remember that here? And again I'm telling that here, this theta in radian. this theta in a radian. And radian formula, what you know very well. Now one formula you should remember that here. You know very well, 180 degree is equal to pi radian. Is it? At least you should remember that here. Is it? Now let's see the students. Some cases are there. So cases of a magnetic field. See the first case. At the center of circular coil. Circular coil means how it will look like? It will look like this. And let's take the current is flowing I. Then you can tell very well at the center how much angle will be there. Just think and tell. At the center the angle will be theta equal to 360 degree or 2 pi. Is it? So magnetic field here at the center is given by mu naught I. Theta is how much here? 2 pi. And by 4 pi r. Is it? So pi cancel. 2 2 is 4. So what will happen that here? Mu naught I by 2r. And even that I have done derivation also before. Okay, so due to circular coil, how much? Remember that we have to use in a question. Mu naught I by 2r. Is it? Similarly, if we talk about here next one, what is given here? See, at the center of semicircular coil. Which kind of coil is this? A semicircular coil like this here. Is it? So semicircular coil here. Just let me draw here. Okay, somewhat looking okay. Na? This is the center O and the radius is R, current is flowing I. So you know very well at the center how much angle will be there here. Na? If I write here like this here at the center here, how much angle? You can tell pi radian or 180 degree. Is it? So what we can write here? See the formula. B equal to mu naught I theta. Theta how much here? Pi by 4 pi r. Is it? So pi anyhow cancel, it will come here mu naught I by 4 r. What is coming due to semicircular coil? Mu naught I by 4 r. Is it? Now after that here students, if we talk about here for the quarter coil, how the quarter coil will look like here? Let me just draw here like this. Quarter coil here. Like this here. Quarter coil is this. Now here how much angle it will make here? Let's take the radius is r anyhow. How much angle? 90 degree, or we can write here pi by 2 radian here. Is it? How much? Pi by 2 radian. So here what we can write here, see here, B equal to mu naught I theta. Theta how much here? Pi by 2 by 4 pi r. Is it? Just cancel out the things and all that. It will come here what? Mu naught I by 8 r. Is it? So kindly see very well. So what we have seen due to circular coil mu naught I by 2 r. Due to semicircular coil, mu naught I by 4r, and due to quarter coil, how much here? Mu naught I by 8r. Okay, remember that here. Is it? Now after that here students, we will just see here some magnetic field calculation based questions. That is important. Is it? So here, let's take part 1 is given here. Is it? We will see some 5 parts are there. We will see one by one, but you are going to learn a lot of things. Is it? So see here. Here remember that here whenever we are solving this kind of questions, like this kind of arrangement is given and we want to calculate magnetic field at the center O. Okay. So to deal with this kind of questions, we have to make the sections. Let's take this section 1, section 2 and section 3. Is it? Now you first guess due to which sections magnetic field will be 0. So you can see due to section 1, this is observation point is along the length of the current. Similarly, this observation point is also along the length of the current for section 3. That means due to section 1 and due to section 3, magnetic field how much? 0. Is it? Because that I have told you in the special condition. So due to B01 and due to B02, how much is there? Magnetic field is 0 because observation point, that means O, is along the length of the current carrying conductor. Similarly, if we talk about the section 2, so B02 is given by which one? Semicircular loop, radius r. So what we can write here, see, remember the formula. Formula remembering very important. Mu naught I by 4r. Direction, all the fingers along the current, no, palm towards the observation point, thumb inside. Is it? And here I will follow this method here. This is x-axis, this is y-axis, outside of the board means z-axis, and if we talk about here inside of the board, it will be negative z-axis here. Is it? So x-axis, y-axis, outside of the board, positive z-axis, inside of the board, negative z-axis, and along the negative z-axis, what is the unit vector? Minus k cap. Is it? So as the thumb is going inside, I will write here minus k cap. So now students, what is the total magnetic field? Total magnetic field means this is a vector sum. So B01 plus B02 plus B03. So anyhow, B01 and B03 is 0 only. So what is the answer? Remember that students, mu naught I by 4r and here how much is coming here? Minus k cap. Now this is the magnetic field due to the first case here. Now first case, is it correct? Now students, after that here, if we'll go for the next one, no? Second one. So here also what going to do? We are going to take the section 1, section 2, section 3. Anyhow, due to which sections magnetic field is 0, you can see very well here, na? Section 1 and section 3. For these sections, observation point O is along the length of the wire here, is it? So what we can write here, due to section 1 and due to section 3, the magnetic field is 0, is it? Now after that, students, due to section 2, what is the magnetic field? Here you can see 3/4 of the circle is there, no? 3/4. So you know due to 1/4 mu naught I by 8r. So due to 3/4, 3 mu naught I by 8r. Even I can use the formula also like this, you see. Mu naught I theta. Theta how much here? 270 degree or 3 pi by 2 by 4 pi r. So pi cancel, number of things will be cancelled. So what we can write here? Remember that here? 3 mu naught I by 8r. Is it? Direction? See, my current now, here current was what? Like this, clockwise, but now current is anti-clockwise, is it? So my thumb is coming which side? Outside here, is it? So if I write here the total magnetic field, B naught means B naught 1 plus B naught 2 plus B naught 3, is it? But you know very well, B naught 1 and B naught 3 is anyhow 0, no? This is 0, this is 0, is it? So what will come? Only B naught 2 will come here. So 3 mu naught I by 8r, and which unit vector? Outside means k cap here. What will come here, students? It will come here outside here, is it? Just let me write here. So see here, in how much beautiful way we have done these two situations, is it correct? Now students, after that, let's see here this scenario. No? This scenario is there, no? Little bit looking tough, but not that much here. See, so here also I'll make here the sections, is it? So let me make here the sections. Depending upon our intelligence, we have to see the section. Section 1, this is flat line. Section 2, this is section 3, and let's take this is section 4, is it? Now students, you can see due to section 2 and section 4, just draw here the dotted line here. Now observation point is along the length of current carrying conductor, is it? That means what will happen that here, due to section 2 and due to section 4, what will happen? The magnetic field will be 0, is it? Now students, after that, if I talk about here, let's take section 1. So section 1 means what we can write here? Semicircular coil. So mu naught I by 4r1. Magnetic field in which direction? See, the current is like this. So thumb is going this side? Inside. So I can write here minus k cap here, is it? Similarly, if I write here due to section 3, no? So what will come here again? Semicircular. So mu naught I by 4r2. Now current is going this side like this. So thumb is coming this side? Outside here, is it? That means here we can write here k cap here, is it? And you know very well, students, here the magnetic field, which magnetic field will be more? Anyhow, R1 is less, so magnetic field B naught 1 will be more, is it? So what we can write here, see, this total magnetic field B naught, that means B naught 1, B naught 2, B naught 3, B naught 4, all this, is it? So when you will simplify this, remember that here, I will write here mu naught I by 4, and here I will write here minus k cap, and it will become here, remember that here, 1 by R1 minus of 1 by R2. Is it? When you will simplify this, you will just get it here, is it? Because due to radius R1, magnetic field will be more, resultant magnetic field at point O will be inward. That's why I have written like this, is it? Great. Now, if we'll talk about here the next one here, students, see, the next one. Here also, see here. Here also we have to make the sections, no? We have to make the sections here. Let's take this is section 1. Let me change here the color. Section 1, section 2, section 3, section 4, section 5. Now like this current is flowing. We need magnetic field at point O, is it? That means what we can tell me due to which sections magnetic field will be 0, because see, observation point O is here. That means due to section 2 along the length of the observation point, due to section 4 along the length of observation point. That means what will happen that here, see, due to section 2 and due to section 4, magnetic field is coming how much here? 0, is it? Now if we talk about here the resultant magnetic field will be due to which sections? 1, 3 and 5, is it? So see, 1, 3 and 5, na? Because others 2 is 0. Na? So now you think here. This is R, this is R, this is R, is it? And what is the formula? Mu naught I theta by 4 pi R is the radius, is it? So see, if we talk about here the section 1, so see here, mu naught I theta by 4 pi, is it? Total radius how much here? R, R, R. Total how much here, students? 3R. 3R. Direction which side here? You can see outward, so we'll write here the K cap. K cap, is it? This is the thing. After that you have to just simplify this. I am just telling the basics. Plus, due to section 3, this is the section 3 again, right here, see, mu naught I theta by 4 pi, how much radius? This R, total how much here? 2R, is it? 2R here, no? And here magnetic field in which direction? See, put your fingers along the current, thumb is going which side? Inside. That means I can write here minus K cap, plus B naught 5 here, B naught 5, no? This one here, 5th section, how much radius? Radius R, so we can write here, see, mu naught I theta by 4 pi R, and see here, again which side? Outside here, K cap here, is it? So students, you have to just simplify this and you will get the magnetic field at the center, is it? So see here. Now students, the last case is this one, little bit complex case, but anyhow, we can solve very easily, is it? So see here, it is looking like this. We have to first think the sections. Here you can see, this is the quarter now of radius R. This is the semicircle of radius 2R. This is the quarter of radius 4R. And this section is along the observation point O, and due to this magnetic field will be 0, is it? Like this we have to decode the question, is it? So what can I write here? See, one by one I will take here, see here students. So let's take, this is the section 1, section 2, section 3, section 4, section 5 and section 6. Is it correct? First, second, third, fourth, fifth, sixth. Now students, magnetic field due to which sections will be 0? See the diagram and tell. Due to section 1 and due to section 5, because observation point is along the length of the current carrying conductor, is it? That means we can write here, see, B naught 1 is equal to B naught 5, and here how much here? 0, null vector. Okay. After that, if we talk about here the resultant magnetic field at the center is due to which sections? Due to section 2 left, plus, and one more thing is there. See, due to section 3 also magnetic field is 0, is it? So see, due to 3 also it is 0. Now, so 1, 5, 3 magnetic field is 0. What is the left? 2 is left, 4 is left, and what is left here, students? 6 is left here, is it? So now we are going to see one by one here, is it? Now, see, magnetic field at the center. Now, one by one we are going to see. Basic we should know very well, basic. Now, so see here, first one we are going to see due to section 2. Which one? Quarter coil is this. So due to quarter coil, magnetic field mu naught I by 4R, is it? And radius is also R, so we can write here, see, mu naught I by 4, radius anyhow R, magnetic field in which direction? You can see all the fingers along the current, palm towards the observation point, thumb is outside, is it? So I can write here mu naught I by 4R K cap, is it? Now after that, again you see this, again quarter is this, quarter. So again mu naught I by 4 into radius, mu naught I by 4 into radius how much here? You think the radius how much here is, students? 3R, is it? So I will write here, see, 3R here, is it? And mu naught I by 4 into 3R, is it? And the magnetic field in which direction? Outward direction. No? So see, let me write K cap here. No? Basics. Now after that, what is given here? See, this semicircle is this. Due to semicircle, what is the magnetic field? Mu naught I by 4R. No? Mistake happened. Quarter means 8. No? Quarter means 8. No? Circular coil mu naught I by 2R, semicircular coil mu naught I by 4R, quarter coil mu naught I by 8R, is it? So here also 8, here also 8, because quarters was there. Now semicircle. So due to semicircle, what will happen here? Now see, mu naught I by now 4, is it? And radius how much here? You can see very well, 2R here, is it? So we can write here the students 2R, is it? Now students, so correct? Mu naught by 4 into 2R into K cap here, is it? Let me check one by one. Due to section 2, radius R, I have written. Due to section 4, how much radius? 4R. But what I have written 3R, just let me make here the 4R. How much this here students? 4R here, 4R. No? See, 4R. And here radius, how much here? 2R. So here also 2R, is it? Now what we are going to do? We are just going to simplify this here. So see, mu naught I by R into K cap here. Now we have taken outside. So what this will become here? See, 1 by 8. No? This 1 by 8. Here how much here? 1 by 32, because 8 into 4, 32. And here also what will happen that here students? 1 by 8 here. Is it? Now what will happen that here? See, mu naught I by R K cap, take the LCM. Let's take LCM is 32. Is it? So 8 4 is 32, 4 1 is 4, here 1, and 8 4 is 32, 4 1 is 4. Is it? So what this will become that here? 4 plus 4, 8 plus 1, 9. So we can write just see 9 mu naught I by 32R into plus K cap here. Is it, students? So just kindly say very well. No? So students, I hope so. This video of the Biot-Savart Law applications and the questions is very clear to you. Keep studying, keep growing.